So we've worked a lot with linear equations, so having something that is y equals mx plus b, where m is the slope and b is our y-intercept. Here we're just going through linear functions. That's really the wording that's changing, is that they're linear functions instead of equations. However, they operate the same way. It's just our notation is changing a little bit, and using the term function brings through this definition that for every input there's exactly one output. So a lot of this will be review of things we already know. It's just applying it with our new notation from when we learned about functions. So where we usually have y equals mx plus b, what we'll be seeing now is that we're defining a function f of x is mx plus b, but it still holds true that m represents slope and b is the y-intercept. Now, finding slope, what we used before was if we had two coordinates, we would take the difference in the y values over the difference in the x values. That's still true here too. We're just changing our notation, so it's f of x2. So we have our input of x2 and our output of x2, and input of x1, output of x1. So really, same thing as those are y values for these corresponding x coordinates. Alright, let's look at finding slope in three different ways, from a table, a graph, and a word problem. So another way that we can talk about slope is that the numerator is looking at the change in y, and for change in something, we can use this symbol delta, so it just means change. So we look for this change in y over change in x. So what's the change in the the change in the outputs over the change in the inputs. So if we're looking at a table, what we could do is if we have our values for t, so those are our inputs, so over here we could find our change in x, or in this case our change in t. And on the right hand side with these values of f of t, we can look at the change in the outputs. Now finding this change, what we're going to do is figure out what's the change as we move point to point here. So -9 to -6, that requires adding 3. -6 to -3, also adding 3. We're going to see it's going to be the same across the entire table. Then we're going to do the same thing for the outputs. And if we look at the change in output, so to get from 14 to 10, we would need to subtract 4. And same thing, subtract 4, subtract 4. So notice with this, our change is always the same. For the inputs, we're always adding 3. For the outputs, we're always taking away 4. And that's a characteristic of a linear function. That's the idea that our slope is constant. It's not changing. This rate of change stays the same. So if our table started showing different values occurring as we went along, that would be a hint that it's not a linear function. But because it's the same, we do have a linear function. So what we're going to do is take the quotient of taking that change in f of t over the change in t. So the change in outputs over change in inputs. And what we saw for the change in the outputs is a -4 each time over change in t, which is a +3. So our slope is 4/3. So that's how you can see that from a table. From a graph, we just need two coordinates. So I have this nice coordinate 0, 5, and then I have this coordinate 4, 0. And what I would want to do is kind of the same idea, was the change in the output over change in input. And to see the change in the output, what I would do is think about how could I walk to the second coordinate. So we would need to go down 5 units. So that's a -5 since we're going downward. And then move to the right, which is a positive direction. And that's +4 units. So for our slope here, we would take that change in the y values, which is the -5, over that change in the x values, which is the +4. So for this, the slope is -5/4. Alright, and then for a word problem, in 2003, a town's population was, sorry, typo, 1,431. By 2007, the population had grown to 2,134. Assume the population is changing linearly. So what we have here is a time and a population, and time and population. So this is like having two coordinates. So we have that 2003 goes with a population of 1,431, and 2007 goes with the population of 2,134. So what we can do to find slope here is take the difference in the populations, so that 2,134 minus 1,431 over 2007 minus 2003. And then we plug that into a calculator. I'm going to jump over to the Desmos calculator so I can show you how to plug this in. So in the Desmos Scientific Calculator, I really like this button, this A over B in the upper right hand corner here, because it separates your fraction for you. So you don't have to worry too much about layering your parentheses correctly or making sure that your order of operations are right. So we'll have 2134 minus 1431 over 2007 minus 2003. And we get our answer of 175.75. All right. And we'll talk about interpreting that later on. For now, we're just about calculating slope. But when we do get to interpretations, something that's going to be important is thinking about what direction is our slope sending us. Are we increasing, decreasing, or staying the same? So if your slope is positive, that's when our function is increasing. So we can see that up above here with the table. That's a positive slope. So what that's telling us is our output values are, I paused there because I made a mistake. Up above, I didn't carry the negative down, and that's where it's so important to not forget our negatives. So this is negative, which makes sense because when I look at the table, as the x values get larger, our outputs are getting smaller and smaller and smaller. Same thing with the graph. This has a negative slope as well, and that shows a decreasing graph because as we're reading to the right, the y values are getting lower and lower and lower. For our word problem here, it's positive, and it's the idea that as time is passing, our population is growing. So we're seeing this increasing. So positive slope, negative slope, and then if we get a slope of 0, that's where it's just constant. So in terms of a graph with a constant function, it's just going to graph a horizontal line. The idea that our y values aren't changing. They're staying the same. They're staying constant.